Hey everyone, moving into chapter 22 here, which is electric fields part 2. So we looked at electric fields and the forces on charges in the last chapter, but now we want to focus on electric fields around different shapes and different types of charge distributions. The first thing I'm showing you here is that lightning does strike the same place more than once. Tall objects can get hit several times a year, so that's one gigantic myth to get out there. The second thing we need to do is calculate electric fields using calculus like we did in class. Linear charge density is known as lambda, that's charge per unit length. Surface charge density is when you have charge over top of an area, that's sigma. And volume charge density is rho, and that's when you have charge throughout an entire volume. Mainly that would be if we had an insulator that was charged all the way throughout. So let's look at this example. We've got a line of charge, and we want to find the electric field strength along the z-axis. So not in the x-y plane, but along the line of charge. Let's show you how we can calculate and add up the electric field from every single charge in this picture. Alright, so I'm going to make the origin right here in the middle of the rod, and you can see the rod is positively charged. So if I want to calculate electric field strength, finding my changing electric field from every single piece of charge is K times Q over R squared, just like we had before. But now we write Q as dQ for all the little infinitesimally small pieces of charge along that line. Or since we have charges distributed along the line, so lambda is the charge per unit length there. So if I want to solve for dQ, dQ is the derivative of charge, and lambda is a constant, and it's going to be multiplied by dl. In this case, I'm going to call it dr, along any r distance from point P to a location on the rod. That'll be my r distance. So if I substitute dq in, my integration becomes k lambda, integrating from dr over r squared. So that's nice. We've already don't have to eliminate anything else. The k and the lambda came out since they're constants. So I'm integrating 1 over r squared dr. And 1 over r squared becomes k lambda 1 over r. And I'm going to evaluate the between my bounds of r1 and r2. So if I put in my two bounds, the electric field strength along the z-axis here is k lambda 1 over r2 minus 1 over r1. So I just need to know the distance from my two locations, r2 being this distance right here from the point to the front of the rod, and r1 being this all the way back here. And you can see that if I want to know in terms of not r but the z position, I can look at putting r1 and r2 in there in terms of z plus half the length and z minus half the length if I want to get the actual z position from the origin, which I said was right here in the middle of the rod. So putting that in, you can expand this. So if we're trying to find the electric field along the z-axis, this is the formula you can use. But they always throw in some stipulations, like what happens when you get closer to the rod, or what happens if you get far away from the rod. There's a solution that if z is much greater than half the length, what happens is that the electric field turns into k q over z squared. So really the line of charge becomes a point charge if you get far enough away from the line. So that distance is so much greater than how big the rod actually is that it actually can just be treated as a point charge rather than having to deal with the distances and lengths of rods. So that brings us to an infinite line of charge. And what do I mean by an infinite line of charge? I mean that you've got a line that goes out so far in every direction, kind of like what you're seeing here in these drone videos of someone flying over an airport. When a drone's flying over a runway, you can't tell where the beginning of the runway is and where the end of the runway is. It just looks like it goes on forever in all directions. And that's what we mean by this infinite line of charge. That no matter where you move away from the line doesn't look like it has a beginning or an end. It's an infinitely long line of charge. So let's set this up and show how we could solve. So here's our setup. We've got an infinite line of charge here, and we are a distance y from the rod. So the question is, what is the electric field and which way does it point? Well, you've got to take different pieces of the rod. Like if I take a section of the rod right here and I add up that little piece of charge, it is technically an r distance away from the line. And the electric field would point off in that direction. So the electric field from the left side of the rod would point up and to the right. But if I take a little piece of charge from the right side of the line here, that little piece of charge here is another r distance away and would point off in this direction. And if you look at those two electric fields, they're pointing in opposite directions, and it looks like they have components. They've got x components here, left and right, and they also have vertical components up on both electric fields. So what you could say about the electric fields in the x direction is that those two are equal, which means that the electric field left and right is going to cancel out. I don't need to calculate for the x component. What I'm going to do with my y components here is I'm going to combine them. I have to find the electric field in the y direction so that I can figure out what the net total field is that is pointing straight up. So the net field from an infinite line of charge here is pointing directly away from the infinite line. So let's see how we can calculate that electric field strength. So this setup should look familiar again. We have it set up where we've got kq over r squared times the sine of theta for every little piece of charge as we go up and down that rod. So technically, our charge is really going to be dq as we go along that line. And that means that our charge is going to be along the length. So lambda is charge per unit length, which means that I could write lambda as, or dq as lambda times dl, or in this case we'll call it dx again, since the rod's lying in the horizontal plane. So I can put that in for dq, which leaves me an integration dx over r squared sine of theta. The problem with this setup, just like we saw today, was that x changes, r changes, and theta changes all the way along my rod. So the angle is going to be different everywhere, the r distance is going to be different everywhere, and the x distance to each of those points is going to change for every single piece of the rod. So you've got three changing variables again. So if we have three changing variables, we want to write this in terms of one changing variable. And I'm going to make the case again for theta. All three are changing as we integrate, so we want to write our integration in terms of just one changing variable. So I'm going to make that our theta here. But looking at our triangle here with x, r, and theta, there is something that's constant. And what's constant is this distance right here, y. So if I write trig functions for sine, cosine, and tangent in terms of that constant y, that can help me eliminate some of these variables like x or r or theta. So if I write tangent of theta is going to be opposite, which will be y over the x. And if I want to solve for x, because I need to get rid of that dx in my electric field equation, electric field is going to be y over tangent, or you could write that as y cotangent. And when you have y cotangent, I need dx, not just x. So dx becomes y cosecant squared theta d theta. Now I did drop a minus sign in there. Technically, for the first triangle I made, my x direction was negative, which would make y cotangent negative, which would then make dx y cosecant squared theta d theta a positive value. So I'm going to put dx in my equation. If I wanted to eliminate the r, well, I'm going to use sine, because sine of the angle is going to be the opposite, which is y over distance r from the rod. Solving for r gives me y over sine, or y cosecant. And I really want r squared, so I've got to square everything on both sides of the equation. So r squared, y squared, and cosecant squared. I'm now going to take r squared and dx and put them right here for dx and r squared. And you're going to get some simplification here. So there's our equation with everything subbed in now. We want to pull out constants as we go through this. things that are constant and things that can cancel, I'm going to start crossing off here, which is going to leave me a sine theta d theta to integrate. And I'm going to integrate that from two specific places this time, since this is an infinite line of charge. Two specific places are when I'm so far over here on the left side of the page that my theta is almost perfectly flat. So my first bound is going to be 0, and my second bound is going to be when I'm so far over this way on the right that pretty much the electric field points perfectly flat backwards. So 180 degrees if you want to do that, but I'm going to write it in terms of pi. So I'm going to go from 0 to pi on my integration here. So now we need to integrate sine of theta. Sine of theta gives us negative cosine theta, and we're going to evaluate that between our bounds of 0 and pi. So if we put that in there, we're going to get negative cosine of pi minus a minus cosine. So we're going to get minus cosine of pi minus a minus cosine of 0, or plus. Well, the nice thing about cosine of pi, if you think of your unit circle, that is actually negative 1, plus cosine of 0 actually is positive 1. So minus a minus is plus, 1 plus 1 is 2. So the electric field strength away from an infinite line of charge is k lambda times 2 over y. And if you look at the top there, everything is constant, the lambda, the k, and 2. So really, the electric field strength dies off by a 1 over y relationship. So when you are near an infinite line of charge, the infinite line of charge has a strong electric field very close, but as you start getting further and further away, the electric field will die off as a 1 over y relationship. So there they're showing you point charges versus line segments versus infinite line. You can see a point charge is a much severe slope. That is a 1 over r squared. Well, the infinite line is just a 1 over r relationship. So it brings us to our last one here, the ring of charge. And when we're looking at the ring of charge here, the charge is around the entire ring. Let's call it positive again. And you can see that the electric field from that tiny dq is pointing down to the right. But if I take charge from the bottom of the ring, here, the electric field points up and to the right. So if you look, you can see that the perpendicular components, up and down, are going to cancel. So all I really need to care about here is the component that's along this z-axis. So let's draw this out for ourselves and see if we can calculate the electric field from our ring of charge, the one ring to rule them all. Okay, so in our setup here, I'm taking my dq as my little segment of charge way up here at the top of the ring. It's an r distance from the ring, it's a z distance from the center of the ring, and a is the radius of our ring. So you can see my electric field's broken into a parallel and a perpendicular component here. The perpendicular component's going to cancel because of the charge at the bottom of the ring, so I actually don't have to worry about it. So all I'm going to really have to worry about here is the cosine component when I solve for electric field. So the electric field along the z direction will be k dq over r squared times the cosine of theta, since I only need to worry about that cosine component. One thing we can do here that we didn't do in the past is let's try to get rid of that cosine of theta there. That cosine of theta, the angle for my electric field is actually the same angle right here. So if I look at cosine of my triangle next to the ring is the z over r. So I'm going to put that in for cosine here. And if you look at that, what that's going to give me is kz, since z is now a constant, over r cubed, which I'm going to pull out as well because r is a constant even if I'm looking at the bottom of the ring here. That's the same r distance away, it's the same z distance away, so that leaves just dq behind in my ring. So this is going to be an easy integration. I'm going to integrate from no charge up here at the top to entirely around the ring, and the entire ring has a total charge of q. So I'm going to integrate between 0 and q for dq, so q will just become charge. So the electric field around a ring of charge here is going to be KQZ over R cubed. Now, they may want you to solve for the electric field in terms of actual constants. R is just an arbitrary distance from the ring to that point P. So if I go back to my triangle here with A, Z, and R, I can use some trigonometry and say that R is the square root of A squared plus Z squared. And so that means my electric field then would be KQ over times Z all over R cubed, which is really A squared plus Z squared to the 3/2 power. So this is how you can calculate the electric field from a ring of charge, knowing the radius of the ring, the distance you are from the center of the ring, and the amount of charge on that ring. And we can also look at some limits on this, like what happens if Z is much, much, much bigger than the radius. So what if it gets so far from the ring that we can't even see the radius anymore? Well, that means that the ring of charge, or the A in our equation, pretty much goes to 0, which gives me Z squared times the 3/2 power, which will knock out the square. So I really have Q, or KQZ over Z cubed, which means I can knock out a Z cubed, and I would be left with KQ over Z squared. So when I'm very, very far away from the ring, I can't really tell what's going on. It looks just like a point charge again, and I get my KQ over R squared again. Well, what if Z equals 0? Well, if Z equals 0, that means I'm in the middle of the ring there. And if Z equals 0, if I put 0 right here, the electric field becomes nothing. Which, if you look at the picture, it'll make sense. If I put a charge right here in the middle of the ring, that charge is going to feel no force whatsoever. It's going to feel pushes from up, down, left, and right, and the field's going to perfectly cancel out. So the electric field strength grows away from the center of the ring, but as you get further and further away, eventually it's going to turn into a point charge, and the point charge will just be 1 over, or KQ over R squared. So what we've been doing here is calculating electric fields using calculus. There must be a better way than trying to integrate the electric field throughout all these different distributions. And that new way is coming soon.